We just started talking about using standard deviation and how we can calculate it, but even more common than using just the standard deviation alone is for us to calculate what we call the confidence interval, and for us to do various different statistical tests. So, in order to calculate the confidence interval, we also need to define our first statistical test, and there are many. The one that we are going to use most in this class is called the student's t. And student's t allows us to use a small data set because we talked about how with standard deviations, they're most commonly used with really large data sets, but we don't always have access to a large data set. Sometimes we only are able to take, say, 3 measurements. And in that case, if we have a Gaussian curve and we are imagining that our curve is something like this, we don't really have any clue what those 3 data points are. They could all be really close to the mean, but they could also be super spread out, and we wouldn't necessarily know. So the student's t allows us to do some averaging based on the Gaussian curve and based on a limited number of data points in order to decide whether our measurements are statistically equivalent or not. So the student's t is sort of a funny name, and I was always kind of curious about what it was. It was developed in 1908, and I was also curious about why it was called the student's t, by a guy named William Seeley Gossett. You don't have to remember his name, but what you might remember is that he was working at the Guinness Brewery at the time. Whether or not you like Guinness, it is an interesting factoid. So he was really interested in dealing with statistics for small sample sizes like 3, and he was looking at how to look at the ingredients that they were using for brewing the beer, even with relatively small sample sizes or relatively small number of experiments, to predict whether or not the replicate trials of making beer were going to be equivalent to each other. So this student's t came out of that statistical work. So I'm first going to define the confidence interval. And the confidence interval, we're going to use the Greek letter mu again. Mu. I guess actually it makes more sense since we have a convenient kitty name, right? So it sounds like what your kitty says, mu. And we're going to calculate mu based on the average plus or minus student's t, which is this t here, the standard deviation divided by the square root of the number of data points that we have. So all of these should be pretty familiar. Student's t, I'm just going to draw a little line here. So here's my standard deviation. And here is the mean. So we use the information that we have here to look up the student's t in table 4.2 in the Harris book. So I'm going to switch over and show that one to you. As we can see from table 4.2, we have several different columns. We have the confidence level, and we also have the degrees of freedom. So this is our columns and our rows. So depending on what confidence level we have, we're going to choose the appropriate confidence level that we want and then however many degrees of freedom we have, and remember this is n minus 1. So when we think about the confidence level, this is sort of a strange name, but if we look at this, we have a percent confidence level, and what we're seeing is that we are choosing a confidence level, and whatever that confidence level is, that's our percent confidence that the measurements that we're talking about are statistically equivalent. So we'll look at some examples to try and illustrate that. One of the other things that I want you to notice about table 4.2 is that the percent confidence t-values, they increase as we go to higher confidence. So let's go ahead and do a calculation, and we'll do a couple different calculations, right? We'll do a calculation at the 95% confidence level, and then we'll do a calculation at the 90% confidence level. So let's go ahead and take a minute with those equilibrium constant values from PChem that we were earlier calculating the mean and so on. So we calculated that the mean was 0.00013, or 1.3 sub 0 times 10 to the minus 4, and we calculated a standard deviation of 7.8 times 10 to the minus 5, and there were 8 data points for that. So if we calculate this at the 95% confidence level, we can calculate the 95% confidence interval. So if n is equal to 8, that means our degrees of freedom is equal to 7. And if we look on the table, we should find a t-value of 2.365. It's a good idea for you to pause the video for a second, go look up the t-table in the Harris text, and verify that what I'm telling you is true. Hopefully you found that and I didn't have a typo. So let's go ahead and calculate our confidence interval. There's our equation. All the equations in this class will be in an equation sheet, so you don't have to memorize them. So this is 1.30 times 10 to the minus 4, plus or minus, plug in that t-value, 2.365 times 7.8 times 10 to the minus 5, that was our standard deviation, divided by square root of 8, because it's square root of n, not square root of the degrees of freedom. This is an easy place to get mixed up, so we'll try not to. So if we calculate that through, we get 1.30 times 10 to the minus 4, plus or minus 6.5 times 10 to the minus 5. So we are saying that we're 95% confident that all future k values that we measure are going to fall into this window, or at least 95% of them should. One thing to notice is that if we choose a different confidence level, so for example a 90% confidence level, we're going to use t is equal to 1.895 instead of 2.365. So when we calculate our confidence interval for this particular t-value, we have the same mean, of course. So we'll have 1.30 times 10 to the minus 4 plus or minus 1.895, 7.8 times 10 to the minus 5. So this is mostly the same except for that t-value. And what you'll notice here is that our interval is a little bit narrower. Okay, so if this is our mean value, then my 95%, I better make it bigger so that I can reliably draw 2. Okay, so my 95% confidence interval would be plus or minus this amount of 6.5 times 10 to the minus 5, right? But the 90% confidence interval is a little bit smaller. So when we go to a lower confidence interval or a lower confidence level, we're actually taking a smaller window. It sounds sort of like the opposite, but a 90% confidence interval is actually taking a smaller window. And this is why it's only 90% confident. I've made myself a narrower target, if we think about that, right? That my 95% confidence interval is a target this size, but my 90% confidence interval is a little bit smaller, and I have to hit that smaller target, which means that I'm probably only going to hit it 90% of the time instead of 95% of the time hitting this larger target. So when we use student's T and we calculate the confidence interval, there are actually 3 separate cases. And I'm going to outline all 3 of them here, but in this video I'm only going to talk about the first one, and then I'll save the other ones for later videos. They'll still be in this, this week. I just don't want to make a video super long. So our first case is we compare the confidence interval to a standard reference material. And I'll go through some examples of how that might look. So that's case 1. In case 2, we're going to take replicate measurements in 2 or more trials and see if the trials are equivalent. So case 2, I might be using the same technique 2 times, or I might be using 2 different techniques, but they're all a whole set of samples or a whole set of measurements on the same sample group. And then in case 3, this we are for sure using to compare different techniques. With a series of samples. So rather than just testing like one water sample that has a certain amount of an analyte in it, and I test for that analyte multiple times, we're going to take, say, 8 different water samples and test all of them separately, okay? And we're going to use 2 different techniques for each of those different samples. So we're going to compare different techniques with a series of samples and see if the techniques are equivalent. Okay, so I'm going to give a simple example first, and then we're going to look at a literature example and see if we can apply case 1 to it. Okay, so the first example that I'm going to give you is an example from my graduate school. I did a lot of powder X-ray diffraction. And this is just sort of background material. It's not really critical. But on the powder X-ray diffraction, you're analyzing solid samples to find out what the material is that's in them. And one of the important questions that we ask is my XRD, X-ray diffractometer is what that stands for, calibrated? Because if it's not calibrated, then it's not going to give me the sample peaks where they need to be. And unlike techniques like gas chromatography and HPLC. You may or may not know what those are. It's okay if you don't. Those ones, the peak locations are just kind of relative. But in an X-ray diffraction, the peak locations are very specific, and they need to be exactly in the right location. So the question of whether or not my X-ray diffractometer is calibrated is a pretty important one. So we used a standard reference material to find out whether or not our instruments were calibrated. And the one that we did was a silicon sample. It was a very fine powder, and it is certified by NIST, the National Institute of Standards and Technology, to have a lattice size that is equal to 5.431179, I just looked it up, plus or minus 0.000008 angstroms. Angstrom is a unit that is a little bit specialized. It's mostly used in things like crystallography, but it's really convenient because most molecules and atoms are sort of on this angstrom scale. So it's 1/10 of a nanometer, or in other words, it's 1 × 10 to the minus 10 meters. And it has this little special bubble of an A with a dot, with a little, or A with a bubble over it as the angstrom symbol. All right, so we purchased this silicon reference material, and then we analyzed it in our instrument. And so let's say that I measure the sample 4 times, and I analyze them. My instrument doesn't have as many significant digits as the standard reference material one that, or the one that they use to create the standard reference material. So let's say that these are the lattice sizes that I get for 4 different runs on the sample. So here's my question. Is my instrument calibrated? So we're going to use case 1. We're going to calculate the confidence interval, and we're going to see whether or not our confidence interval contains this certified value. So does my confidence interval contain the certified value? All right, so our first step is always to pick a confidence level. 95% is a pretty common one, so we'll just go ahead and go with that one. So if I'm picking 95% confidence, we have n is equal to 4. I have 4 data points here, which means that I have 3 degrees of freedom. And I should then have an n value of 3.182. Okay, so what I want you to do is I want you to pause the video. I want you to calculate the average and the standard deviation, and then I want you to calculate the confidence interval. Okay, hopefully you had time to calculate the confidence interval. So when I calculated it, hopefully I did it right, I got an average value of 5.4318 angstroms, a standard deviation of 4 times 10 to the minus 4 angstroms. And then I calculated my confidence interval to be 5.4318 plus or minus 0.0007, or 7 times 10 to the minus 4 angstroms, which means that my interval here goes from 5.43311 angstroms if I subtract 0.0007 from my average, up to 5.4325 angstroms. Okay, so this is my far range. So my question of whether or not my sample is calibrated, or excuse me, my instrument is calibrated, I look at my certified value here, 5.431179, and I look at where my values are here, and I can see that my certified value shows up right over here on the very edge of my range, but it doesn't matter. It's okay, right? It can be at the edge of my range. The important thing is that the SRM is inside my confidence interval. And if that's the case, then my conclusion is that my instrument is giving me statistically equivalent information to the standard reference material, which means that my X-ray diffractometer is calibrated. Okay, so let's go ahead and look at a slightly more complicated example. And this one is one that I found in the literature and I thought it was interesting. Okay, so let's go ahead and start looking at this example 2. Okay, so I was thinking about what would be a fun environmental chemistry example to look at, and my mind always kind of goes and thinks about toxic chemicals in our water, for example. So I started thinking about lead. And if I think about lead, then I think about Flint, Michigan, which is still struggling to try and get good water in its community. Things have improved, but anyway, when it first happened, one of my thoughts, because I teach quantitative analysis, was could we precipitate the lead out? And I looked it up, and there's not really a convenient way to do that that would sufficiently purify it. So I thought, well, maybe there's an easy method for us to test it, right? Maybe we could make a cool lab that would work. Well, it's actually pretty complicated to test for lead in water. And most of the techniques that we use for testing for lead are things like atomic absorption spectroscopy, which we'll talk about more later. So this is AAS. This is one of the ways that we do. And then there's a lot of other even more expensive kinds of methods that we might use. So I managed to find this journal article. I'm going to switch over to it right now. Not that one. Okay, so here's the journal article. It's in a journal called Analytical Chemistry Insights. And it's talking about using this flotation spectrophotometric method. And I'm posting this on our Moodle, so you can take a look at it if you are interested in it. And what it does is it uses these lead ions and alizarin yellow, which is a dye, and it floats a complex between these two, between a water and hexane interface at a specific pH. It sounds kind of complicated, but it's pretty low tech. I mean, most people who are doing any kind of analytical chemistry are going to be able to access water and hexane. They're going to be able to affect the pH. Alizarin yellow is a dye that's pretty accessible. And then they used Beer's law, so they just did UV vis on it. So anyhow, the interesting thing about this is that they list a bunch of standard deviations and statistical results for the sample. So I thought we could take a look at them. So if you have time, go ahead and take a look at this article and feel free to skim through it. I'm happy to clarify. This is not something that I'm super familiar with it, but I can help you interpret some of the information behind it if you're interested. Okay, so all the way down at the bottom, I hope this isn't making you dizzy. Good. We have some analytical information that they collected comparing a sample that they had spiked with lead. So that's the spiking means you put a certain amount of a reagent in there, and then if you know that that amount is present, then you should be able to detect it again. And this allows you to check, just like the silicon standard reference material, this allows you to check your technique and verify that you are able to detect materials at the statistically significant level that you want to. Okay, so I thought this was pretty interesting. They give us enough information that we can actually calculate some confidence intervals. So they have 3 sets of different amounts of lead that they added in nanograms per milliliter. So we have 20, 30, and 40 nanograms per milliliter added to 100 milliliters of water. And then they had some synthetic seawater where they added 40 and 60. So what we can do is we can go ahead and calculate the confidence interval and just kind of take a look and see whether their statistical methods kind of match up with what they're talking about here. So I'm going to switch back over. Here we are. So we can do that calculation. So once again, our confidence interval. So assuming everything is right, they told us there were 7 samples. And if we pick the 95% confidence level, then we'll have 6 degrees of freedom, and T would be equal to 2.447. So let's look at one of their reported values. How about if we just go ahead and start with the 20 was it milligrams? It was nanograms. Nanograms per milliliter of lead 2 plus, and this is the tap water sample. And with 7 samples, they took an average value of 23.05 plus or minus 0.14 nanogram per milliliter, which I think they said was something like 4% relative standard deviation or some such. A good practice would be to just go ahead and calculate the relative standard deviation right now. But we're going to calculate the confidence interval also. All right, so our confidence interval, 23.05 plus or minus, here's our t value, 2.447. There's the 0.14, the standard deviation, over square root of n, which is 7. And so we will get for our confidence interval 23.05 plus or minus 0.05 nanograms per milliliter. Okay, so if we're thinking about our case 1 analysis where we're comparing to a standard reference material, the standard reference material that we are comparing it to is the spike. They told us that this was a standard material and that they put in 20 nanograms per milliliter. But if we think about our confidence interval here, 23.05 plus or minus 0.13 nanograms is 22.92 milliliters, or excuse me, nanograms per milliliter, up to 23.18 nanograms per milliliter. So if we're using case 1 to analyze this, 20 nanograms per milliliter is still like way the heck over that way compared to this interval. It is not in our confidence interval. So if we were going to do a conclusion about the statistical analysis here, we would be forced to say, well, this looks like the spike that we put in, even though we have some pretty high precision, right? Our standard deviation is relatively low. We have high precision, but this is not statistically equivalent to our spiked sample, 20 nanograms per milliliter. And we might even go so far as to conclude that it may contain some systematic error. If you calculate the confidence intervals for the other samples, I'm going to go ahead and switch back over. You will find, unfortunately, that none of the other levels also have the confidence level. The confidence interval that we calculate does not contain this spike that we included here. Now, this does not mean that their results are not important. What it means instead is that they appear to have a pretty good percent recovery, but they have some systematic errors because this is pretty good precision, right? It's a little bit higher of a standard deviation here on this 40 milliliter sample, but all the other samples are really pretty darn good for their precision. So it looks like we have some amount of systematic error that could be corrected then. So that way we would be within our confidence interval. So hopefully you have found this discussion of two different cases, two different examples of case one kind of useful. And we're going to go ahead and stop now and try assignment number 4. And I'm going to have two different kinds of problems in assignment number 4 because our book does not have a ton of different confidence interval examples here. So in the Harris book, Quantitative Analysis, I'd like you to try problems 411 and 420. And then in the Environmental Chemistry book, I want you to look at chapter 1 and try problems 7 and 9 and 11. And these ones are not about statistics. Instead, these ones are ones that are going to try to sort of refresh some of your background knowledge on chemistry and some of the fundamental skills that we're going to be using later on in the semester. And so you may end up needing to do a little bit of review in that review section of the Moodle. And of course, please feel free to ask questions on any of these.